At the end of this video, you should be able to describe the role of models and diagrams in physics. Chapter 1, Section 1, Physics uses models that describe phenomena. Although the physical world is very complex, physicists often use models to explain the most fundamental features of various phenomena. Physicists have developed powerful models that have been very successful in describing nature. Many of the models currently used in physics are mathematical models. Simple models are usually developed first. It is often easier to study and model parts of a system or phenomenon one at a time. These simple models can then be synthesized into more comprehensive models.
Models are used to represent things that are too small to see, such as atoms. Models can also represent objects in the solar system that are too large or far away to observe in certain ways. For example, this model can be used to show how the movements of the Earth, the Moon, and the Sun result in the different phases of the Moon. Scientists and engineers use computers to model systems and processes that are too expensive, complex, or dangerous to test in real life. For example, computer simulations use data related to ocean temperature and weather patterns to predict El Niño events and decide when to evacuate citizens prior to a hurricane making landfall. Models can also be used to represent ideas, concepts, or theories. For example, scientists noted that a rolling object, such as a push lawnmower, veers when it encounters at an angle a surface that slows it down. Light similarly veers when it passes from an easy-to-go-through medium, such as air, into a thicker medium, such as water. Scientists use the lawnmower model to help explain why light might exhibit such a behavior.
When developing a model, physicists must decide which parts of the phenomenon are relevant and which parts can be disregarded. For example, let's say you wish to study the motion of the ball shown in Figure 1-5 on page 6 of your text or on the screen now. Many observations can be made about the situation, including the ball's surroundings, size, spin, weight, color, time in the air, speed, and sound when hitting the ground. The first step towards simplifying this complicated situation is to decide what to study, that is, to define the system. Typically, a single object and the items that immediately affect it are the focus of attention. For instance, suppose you decide to study the ball's motion in air before it potentially reaches any of the other players, as is shown in Figure 1-6 on page 7 of your text or on the screen now. To study this situation, you can eliminate everything except information that affects the ball's motion. You can disregard characteristics of the ball that have little or no effect on its motion, such as the ball's color, for example. In some studies of motion, even the ball's spin and size are disregarded, and the change in the position of the ball will be the only quantity investigated. In effect, the physicist studies the motion of the ball by first creating a simple model of the ball and its motion. Unlike the real ball, the model object is isolated. It has no color, spin, or size, and it makes no noise on impact. Frequently, a model can be summarized with a diagram. Another way to summarize these models is to build a computer simulation or small-scale replica of the situation. Without models to simplify matters, situations such as building a car or sailing a boat would be too complex to study. For instance, analyzing the motion of a sailboat is simplified by imagining that the push on the boat from the wind is steady and constant. The boat is also treated as an object with a certain mass being pushed through the water. In other words, the color of the boat, the model of the boat, and the details of its shape are left out of the analysis. Furthermore, the water the boat moves through is treated as if it were perfectly smooth flowing liquid with no internal friction. In spite of these simplifications, the analysis can still make useful predictions of how the sailboat will move. Models can help build hypotheses. A scientific hypothesis is a reasonable explanation for observations, one that can be tested with additional experiments. The purpose of simplifying and modeling a situation can help you determine the relevant variables and identify a hypothesis for testing. Consider the example of Galileo's thought experiment, in which he modeled the behavior of falling objects in order to develop a hypothesis about how objects fell. At the time of Galileo's work being published on falling objects, which was 1638, scientists believed that a heavy object would fall faster than a light object. Galileo imagined two objects of different masses tied together and released at the same time from the same height, such as the two bricks of different masses shown in Figure 1-7 on page 8 of your text or on the screen now. Suppose the heavier brick falls faster than the lighter brick when they are separate, as in example A. When tied together, the heavier brick will speed up the fall of the lighter brick somewhat, and the lighter brick will slow down the fall of the heavier brick somewhat. Thus, the tied bricks should fall at a rate in between that of either brick alone, as in example B. However, the two bricks together have a greater mass than the heavier brick alone. For this reason, the tied bricks should fall faster than the heavier brick, as in example C. Galileo used this logical contradiction to refute the idea that different masses fall at different rates. He hypothesized, instead, that all objects fall at the same rate in the absence of air resistance, as in example D. Models help guide experimental design. Galileo performed many experiments to test his hypothesis. To be certain he was observing differences due to weight, he kept all other variables the same. The objects he tested had the same size, but different weights, and were measured falling from the same point. The measuring devices at that time were not precise enough to measure the motion of the objects falling in air. So, Galileo used the motion of a ball rolling down a ramp as a model of the motion of a falling ball. The steeper the ramp, the closer the model came to representing a falling object. These ramp experiments provided data that matched the predictions Galileo made in his hypothesis. Like Galileo's hypothesis, any hypothesis must be tested in a controlled experiment. In an experiment to test a hypothesis, you must change one variable at a time to determine what influences the phenomenon you are observing. Galileo performed a series of experiments using balls of different weights on one ramp before determining the time they took to roll down a steeper ramp. The best physics models can make predictions in new situations. Until the invention of the air pump, it was not possible to perform direct tests of Galileo's model by observing objects falling in the absence of air resistance. But even though it was not completely testable, Galileo's model was used to make reasonably accurate predictions about the motions of many objects, from raindrops to boulders, even though they all experience air resistance. Even if some experiments produce results that support a certain model, at any time, another experiment may produce results that do not support the model. When this occurs, scientists repeat the experiment until they are sure that the results are not in error. If the unexpected results are confirmed, the model must be abandoned or revised. That is why the last step of the scientific model is so important. A conclusion is valid only if it can be verified by other people.
A controlled experiment compares a control group with an experimental group. These three groups of frog eggs were exposed to different amounts of ultraviolet light in an experiment designed to test the effect of ultraviolet light on frogs. A variable is a factor in a controlled experiment that changes. In the frog experiment, the variable is the amount of ultraviolet light exposure. All of the other factors in the experiment will be the same for the control group and the experimental groups. This will allow scientists to be more certain that differences in the variable, which is the amount of ultraviolet light exposure, caused any differences observed in the outcome of the experiment.
At this point, you should be able to describe the role of models and diagrams in physics.